Hello everyone, this is section 14.8, maxima and minima in 3 dimensions. So recall back in Calculus 1, we had maxima and minimum in 2 dimensions, so relative max, relative mins, and points of inflection. So you might recall maybe having a graph, something like this, and here was our max, here was our min, and then right in between, this was the point of inflection where the function changes concavity. We say relative max, relative min, because there could be, extreme values here that are max higher than the relative maximum. But notice that the first derivative for the relative mins and the relative max, first derivative, which is our tangent line, is 0. So when we extend this to 3 dimensions, we still have relative maxes and mins, but then we have saddle points as well instead of points of inflection. So if you consider, let me just draw the system off to the side. But I won't draw the graphs on the axes just for simplicity. So you can have something like this maybe, where obviously that's the relative max. At least supposed to be formal here, I should say relative for these as well. But notice that in the y direction, tangent line 0, so the partial with respect to y would be 0, and then in the x direction as well, the tangent line is 0. And that would hold true for a relative min, pretty much the same situation, just upside down, where if you have this relative minimum, again in the y direction, tangent line or the derivative with respect to y is 0, and in the x direction, tangent line or derivative with respect to x is 0. And then we have the saddle point. So this one looks something like a couple parabolas and then kind of joined by a little parabola itself. And right in here would be the saddle point. And same idea. Derivative in the y direction 0, and derivative in the x direction is 0. So that leads us to, and you might recall back in Calculus 1, to find possible max mins or points of inflection, we just took the first derivative and set it equal to 0. But now we're going to define a critical point, and we call those critical points. So here we're going to define critical points, but where the partial with respect to x is 0 and the partial with respect to y is 0, or one or both of the partials do not exist at that point. So then we have the second partials test. You might recall the second derivative test from Calculus 1, where if it was second derivative was positive, it was a minimum, and if the second derivative was negative, it was a maximum. Here it's a little bit more involved. We have this special formula for D, what we call D, and that determines, well, not immediately if you have a max or min, but it determines if it's going to be a max, min, or a saddle point. And D is calculated by taking the second partial with respect to x evaluated at the point times the second partial of y of the function evaluated at that point, and then minus the mixed partial at that point squared. So then we're going to get a number because we're plugging in these x and y values. So we end up with a number. And when we evaluate D, if it's positive, then one of two things are going to happen. It's either going to be a max or min, but that's going to depend on the value of the second partial with respect to x. So if d is positive and the second partial with respect to x is positive, then it's a relative minimum. And if d is positive and the second partial with respect to x is negative, then it's a relative max. If d is less than 0, it's immediately a saddle point. And if d equals 0, the test fails. Obviously, you're going to have this theorem at your disposal, but it's kind of analogous to Calculus 1. I always remembered in Calculus 1, if the second derivative is positive, it means it's concave upward. And so it would look like this, and you'd have a minimum relative min. And if the second derivative is negative, it's concave downward, and that would be a relative max. So it's analogous to that as long as d is greater than 0. But here's an example. So it says locate all relative extrema and saddle points. So we first have to find the critical points. So we're going to take a bunch of partials here. With respect to x, we get 2x. Partial with respect to y, we get negative 4y plus 4. And I think what I'll do here, because if you look at the formula for d, which determines if you have a relative max, min, or saddle point, we do have to involve the second partial of x, the second partial of y, and the mixed partial. So might as well do it right from the start. It's your choice when you want to do it, but I'm going to choose to do it now. So the second partial with respect to x, looking at partial with respect to x, it's 2x, so it's derivative 2 with respect to x. Second partial with respect to y, derivative of negative 4y plus 4 would be negative 4. And then the mixed partial, remember, it doesn't really matter how you calculate the mixed partials because they're going to be equal. But let's say you looked at x and you took it, well, this is exactly what we're saying. If we do xy, we'd have to look at x, and the derivative of 2x is just simply 2. I'm sorry, the derivative, we're taking the derivative with respect to y. We're looking at x, so x is a constant, and the derivative would be 0. Okay, so those we're going to hold off on. First, the critical points. So the critical points are found by setting f of x equal to 0 and setting f of y, f sub y equal to 0. And then we can see we get x equals 0, and here negative 4y is negative 4, so y is positive 1. So 0, 1 is a critical point, and it's the only one. Okay, so now we have to determine what is the value of d. So d is equal to, so let's say at 0, 1, we have that d is equal to, okay, the formula is, okay, I'm not going to use the functional notation. I'm just going to use the subscript notation, just knowing that we're evaluating at this point. But to write out the formula, we'll just say f sub x, f sub y minus f sub xy squared. And so at 0, 1, this is the ordered pair, x is 0, y is 1. For f sub xx, it's just equal to 2, so there's nothing we're really substituting into. But if this were 2x, for example, we'd have to put a 0 in for x. Similarly, for f sub y, there's nothing that we're substituting into. And we just have the -4. And then for f sub xy, it's just 0. So minus 0 squared. So we get that d is -8. And then looking at our theorem, if d is less than 0, then we have a saddle point. So therefore, since this is less than 0, it's a saddle point. Okay, and formally the saddle point is at you could say 0, 1, and some people just say f of 0, 1, but it's basically the value of the function. Plugging a 0 in for x, so that's 0, a 1 in for y, so here we get -2 plus 4, which is 2. So 0, 1, and 2 is the saddle point. Okay, we've got 2 more examples to go through, but I'm going to cut the video short here and finish those 2 examples in the next part. So this was part 1 of section 14.8, max mins in 3 dimensions, and we'll just have to do a part 2 with 2 more examples, and then we'll move on. So we'll see you when you're ready.